Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates.
Hello everyone, I hope you are doing great. In my previous video, I have discussed about Heisenberg's uncertainty principle. In this lecture video, I am going to discuss about introduction to quantum mechanics. So let's get started. The content of this lecture video is as follows. First of all, I will explain introduction to quantum mechanics, followed by interpretation of wave function psi, and then physical significance of psi. So let's discuss in detail one by one. First of all, let's see what is classical mechanics. Classical mechanics describes the motion of macroscopic objects, from projectile to parts of machinery and astronomical objects such as spacecrafts, planets, stars, and galaxies. If the present state of an object is known, it is possible to predict by the laws of classical mechanics how it will move in the future and how it has moved in the past. The earliest development of classical mechanics is often referred to as Newtonian mechanics. It consists of the physical concepts employed and the mathematical methods invented by Sir Isaac Newton and others in the 17th century to describe the motion of bodies under the influence of a system of forces. Now let's see the domain of validity for classical mechanics. The domains of validity are shown in this figure, which are classical mechanics with size far larger than 10 raised to minus 9 of meter and with speed far less than 2.99 into 10 raised to 8 meter per second. Next one is relativistic mechanics with size far larger than 10 raised to minus 9 of meter and with speed comparable to 2.99 into 10 raised to 8 meter per second. Next domain is quantum mechanics with size less than 10 raised to minus 9 of meter and with speed less than 2.99 into 10 raised to 8 meter per second. Next one is quantum field theory with size less than 10 raised to minus 9 meter and with speed comparable to 2.99 into 10 raised to 8 meter per second. Many branches of classical mechanics are simplifications or approximations of more accurate forms. Two of the most accurate being general relativity and relativistic statistical mechanics. Geometric optics is an approximation to the quantum theory of light and does not have a superior classical form. When both quantum mechanics and classical mechanics cannot apply, such as at the quantum level with many degrees of freedom, then quantum field theory, that is QFT, is of use. QFT deals with the small distances and large speeds with many degrees of freedoms as well as the possibility of any change in the number of particles throughout the interactions. When treating large degrees of freedom at the macroscopic level, statistical mechanics become useful. Statistical mechanics describes the behavior of large but countable numbers of particles and their interactions as a whole at the macroscopic level. Statistical mechanics is mainly used in thermodynamics for systems that lie outside the bounds of the assumptions of classical thermodynamics. In the case of high velocity objects approaching with speed of light, classical mechanics is enhanced by special relativity. In case that objects become extremely heavy, deviations from Newtonian mechanics become apparent and can be quantified by using the parameters post-Newtonian formalism. In that case, general relativity becomes applicable. However, until now, there is no theory of quantum gravity unifying general relativity and quantum field theory in the sense that it could be used when objects become extremely small and heavy. So that's why these domains of validity are very important. In classical mechanics, following points are very much important. Classical mechanics is formulated to explain the behavior of macroscopic objects. Motion of macroscopic particles obeys Newton's laws of motion. State of a particle is defined with knowledge of the initial state. It requires knowledge of forces, position, and velocity. Prediction of future state is possible. So these are the very important points in classical mechanics. In classical mechanics, there are several limitations. So let's see one by one. First, in classical mechanics, theories could not explain black body radiations. It could not explain photoelectric effect. It could not explain diffraction patterns of particle beam. Classical mechanics could not explain uncertainty principle. And classical mechanics cannot explain atomic spectra. So these are the very important limitations of classical mechanics. To overcome from the limitations of classical mechanics, quantum mechanics has been introduced. So let's have introduction about the quantum mechanics. As I have explained in my previous lecture videos, light is a mysterious thing processing both particle nature and wave nature. This is very difficult to understand within the classical theory consisting of Newtonian mechanics and Maxwellian electromagnetism. The theory to solve this difficulty is nothing else than the quantum mechanics. To understand quantum mechanics or wave mechanics, one need prerequisites knowledge of Bohr's atomic theory, wave motion, and de Broglie's hypothesis and their respective equations. So in my previous lecture videos, I have already explained all these prerequisites. Erwin Schrödinger was interested in de Broglie's matter wave. He investigated what type of equation does this de Broglie's wave obey, and he developed a wave equation in 1926. This is Schrödinger's wave equation. Today it is simply called the Schrödinger's equation. The Schrödinger's equation is nowadays the fundamental equation of quantum mechanics, which governs the microscopic world. It can be properly compared with the Newton's equation of motion, which is the fundamental equation in classical mechanics. By solving the Schrödinger's equation, all the results of Bohr's quantum theory have been derived, and the mysteries in the microscopic world have been resolved one after another. The study of motion of large objects such as baseballs is called mechanics, or more specifically classical mechanics. Because the quantum nature of the electron and other tiny particles moving at high speeds, classical mechanics is inadequate to accurately describe their motion. Quantum mechanics is the science of very small. It explains the behavior of matter and its interactions with energy on the scale of atomic and subatomic particles. Quantum mechanics is the study of the motion of objects that are atomic or subatomic in size and thus demonstrate the wave-particle duality. So this is the beauty of quantum mechanics. In classical mechanics, the size and mass of the objects involved effectively obscures any quantum effects so that such objects appears to gain or lose energies in any amount. Particles whose motion is described by quantum mechanics gain or lose energy in the small pieces called quanta. One of the fundamental and hardest to understand principle of quantum mechanics is that electron is both a particle and wave. In every macroscopic world of things, we can see something cannot be both, but this duality can exist in quantum world of the submicroscopic at the atomic scale. The heart of quantum mechanics is the idea that we cannot specify accurately the location of an electron. All we can say is that there is a probability that it exists within this certain volume of space. The scientist Erwin Schrödinger developed a equation that deals with these calculations. Such equations are very important in quantum mechanics. The comparison of classical and quantum harmonic oscillator concepts of a single spinless particle is shown in this diagram. The two processes differ greatly. In this animated diagram, the classical process from A to B is represented as the motion of particle along a trajectory. The quantum process from diagram C to H has no such trajectory. Rather, it is represented as a wave. Here the vertical axis shows the real part, that is in blue, and the imaginary part is in red of the wave function. In the panels C to F shows four different standing wave solutions of the Schrodinger's equation. Panel G to H further shows two different wave functions that are solutions of the Schrodinger's equation but not for the standing waves. This is the comparison of classical and quantum harmonic oscillator for a single particle. Now let's see what is wave function. I have already discussed about wave function in my previous lecture videos. Now again let's see in detail. A wave function in quantum physics is a mathematical description of the quantum state of an isolated quantum system. The wave function is a complex valued probability amplitude and the probabilities for the possible results of measurements made on the system can be derived from it. The most common symbols for a wave function are the Greek letters lowercase psi and capital Psi. The wave function is a function of the degree of freedom corresponding to some maximum set of commuting observables. Once such a representation is chosen, the wave functions can be derived from the quantum state. Now try to understand the interpretation of wave function psi. As we know that the matter waves must be produced by vibration of some quantity and are neither electromagnetic waves nor they are sound waves. Thus, what quantity is vibrating to produce matter waves is not clear. Schrödinger represented oscillations of the quantity by a mathematical function known as a wave function psi. Psi represents the wave as a function of position and time. So this is one of very important parameter, that greater is the amplitude of wave function psi, higher is the probability of finding the particle at that position and time. Amplitude can be positive or negative. Therefore, the negative amplitude gives rise to negative probability, which is meaningless. Thus, due to negative probability, wave function psi is a complex mathematical quantity. It has no direct physical significance and cannot therefore be measured experimentally. Now let's try to understand the probability interpretation of wave function psi. A probability interpretation of the wave function was given by Max Born. Born's probability interpretation claims that the probability density that a particle will be found is equal to the square of the absolute value of the wave function. Namely, the probability that the particle will found in the small volume dV as shown in this diagram. Let's consider, suppose a small volume dV is equal to dx, dy, dz with three edges of dx, dy and dz at a coordinate point r is equal to x, y and z in three-dimensional space. So as shown in this diagram, let the probability that a particle will be found in this volume at a time t be p of x, y, z, t into dx, dy, dz. The function p of x, y, z and t is considered as a probability in the unit volume in the neighborhood of the point x, y and z, and is sometimes called the probability density. Hence, here the word probability was used. This, however, does not mean that the particle, that is an electron, exists in a form of a particle or a corpuscle, and this particle moves in accordance with the degree of probability. An electron is neither a particle nor a wave, therefore an electron exists with particle-wave duality. The word probability used above or in this explanation, which denotes the chance that the particle will be found in a volume dV when it is detected. So this is the probability interpretation of the wave function psi. As per the Max Born, the probability interpretation of the wave function, he suggested that The square of the magnitude of the wave function, that is psi mod square, gives the probability of finding the particle in that region. Therefore, the probability capital P of finding the particle in an infinitesimal volume dV is equal to dx dy dz is given by P is directly proportional to psi xyz mod square dV. Therefore, psi mod square is known as a probability density and psi is the probability amplitude. Since the particle is certainly somewhere in the space, therefore the probability capital P is equal to 1. Therefore, the probability can be written as integrations with limit minus infinity to plus infinity psi mod square dV is equal to 1. The wave function psi is in general a complex function, but the probability must be real. Therefore, psi is multiplied by its complex conjugate psi star. Therefore, above equation we can write integration with limit minus infinity to plus infinity psi into psi star dV is equal to 1. Thus, although psi has no physical significance, but psi mod square gives the probability density of the particle, that is probability of finding the atomic particle in that particular region. Now let's see the normalization condition. If at all the particle exist, it must be found somewhere in given region. Inside a wave packet, the particle can be found in the region of coordinates x, y, z. And hence probability density is represented by psi xyz mod square dx dy dz, that is equal to probability density. As particle must be found inside the wave packet, the normalization condition implies that the sum of probabilities over all values of x, y and z must be unity, that is triple integration with limits minus infinity to plus infinity psi mod square dx dy dz is equal to 1. Therefore, the normalization condition where the wave functions are normalized, that is the psi mod square dV, is equals to the probability that a particle will be found in an elemental volume dV. Thus the probability we can write capital P is equal to psi of xyz mod square dV. A wave function should always be normalizable, as it would give us a definite probability of finding the particle in given space or given volume. Therefore, a wave function that satisfies all above mathematical conditions is known as well-behaved wave function, and the equation is nothing but the normalization condition. Now let's see the conditions to be satisfied by wave function. So first condition is psi must be a finite function. The wave function must be finite everywhere. Even if x tends to plus infinity or minus infinity, y tends to plus infinity or minus infinity, and z tends to plus infinity or minus infinity, the wave function should not tend to infinity. It must remain finite for all values of x, y and z. If psi is finite, it would imply an infinitely large probability of finding the particle at that point. This would violate uncertainty principle. Therefore, psi must be a finite function. This is very important condition to satisfied by wave function. Next condition is psi must be a single valued. Any physical quantity that can have only one value at a point. For this reason, the function related to a physical quantity cannot have more than one value at that point. If it has more than one value at that point, it means that there is more than one value of probability of finding the particle at that point. So as shown in this diagram, you can see the position is x0, which has the single value for A and B, which is the probability density. Next condition to be satisfied by wave function is psi must be continuous. The psi function should be continuous across any boundary. Since psi is related to physical quantity, it cannot have a discontinuity at any point. Therefore, the wave function psi and its space derivatives, that is delta psi by delta x, delta psi by delta y, and delta psi by delta z, should be continuous across any boundary. Since psi is related to real particle, it cannot have a discontinuity at any boundary where potential changes. Wave functions satisfying the above mathematical conditions are called as a well-behaved wave functions. The continuity of the wave function at the point x0 is shown in the figure. Therefore, we have important points that conditions to be satisfied by wave functions are psi is related with probability of finding a particle at that space and time. Greater the amplitude of matter wave, greater is the value of psi. Amplitude can be positive or negative. Negative amplitude and negative probability is meaningless. Psi is a complex, but psi mod square is equal to psi star is always real and positive. Therefore, psi mod square can have any value between 0 and 1. Psi mod square is equal to 0, that is particle is absent, and when psi mod square is equal to 1, that is particle is present. Psi mod square represents the probability density. So these are the important points for the conditions to be satisfied by a wave function. On the one hand, in the classical theory, we can precisely determine the orbit or trajectory and the momentum of a particle all over the time by using Newtonian equation of motion. And on the other hand, the Schrödinger equation in quantum mechanics determines the wave function from which we can derive only the probability that a particle will be found somewhere. You may feel that this is not entirely satisfactory. However, this is necessary and sufficient in order to describe the microscopic world. This is sufficient from the point of view of Heisenberg's uncertainty principle. This is all about interpretation of wave function and its physical significance and introduction to quantum mechanics. In my next lecture video, I will discuss about Schrödinger's time independent and dependent equations. So don't miss my next lecture video. Thank you.
Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.